All right, for our first nucleophile type thing that is going to be added to ketones and aldehydes, we have sodium borohydride. So sodium borohydride is called sodium borohydride, but what does that translate to? It's sodium, so Na, and then boro is a boron, and hydride is H4. So think for a second, is this a ionic molecule, a covalent molecule, a mixture of those? Pause it, maybe try and draw what you think that it is, and then come back. All right, we did that. So sodium. Sodium is usually an ionic thing. It's going to be an ionic thing here. So we kind of have sodium plus, and then we have BH4. BH4 is going to be a covalent molecule. And then let's think about, we have the positive right here. How is the positive balanced in this molecule? Well, boron, if we go back to formal charge, so it might actually be a good idea if you're having a hard time with this, to go back and look up what formal charge is, look how to calculate it. But boron has a neutral formal charge when it has 3 bonds, and it's lacking its octet. Here it has 4 bonds. So it actually gets a formal negative charge here. So that's what is balancing that positive charge there. But what we know also is that, taking a step back, if we look at these formal charges, often formal charges are a really good indicator of where and what the charges are. Sodium. Sodium has a full positive formal charge. It's really positively charged in reality as well. But sometimes formal charge isn't as correct in the way that it is demonstrating where the charge is. For instance, here, boron is shown as a negative charge because that's what it would be for formal charge. And remember, formal charge is kind of a bookkeeping tool as much as it is useful in describing how the molecule is reacting or charged. And in this case, it's a little bit off. If you look at a periodic table that has those electronegativity values on it, hydrogen is actually more electronegative than boron. So these BH bonds are actually polarized to the negative charge. So while boron has a negative charge here, well, actually just right over here, boron is actually partially positive. And what that means is that all of our H's are partially negative. And it turns out that sodium borohydride, this complex, the way to kind of think about it chemically and how it's going to react is BH4 is somewhat H minus. So all of that sodium borohydride really boils down to hydrogen with 2 electrons that is negatively charged. That's how it's going to react. How is this different from an acid? An acid has H plus, right? H plus does not have any electrons. So that's a big difference here. H minus, this is a nucleophile. H plus, that would be electrophilic. It would be an electron acceptor. This would be an electron donor. So very, very different things. Back to kind of filling in our blanks here. Boron, we talked about way back at the beginning when we were doing formal charges and Lewis structures, and it's a unique element that is stable. It's allowed to not have an octet in Lewis structures. It's stable with 3 bonds or with 4 bonds. So it has 4 bonds here. It's stable there. It's got an octet. But often we see B having only 3 bonds. And actually, hydroboration oxidation, something you guys saw in both chapter 10 and 11, is BH3. So now we've seen BH4. BH3 was another thing that we've seen. Blank is the most mild form of blank. It only reduces blank. So this is not something you'd be able to guess yet, but boron, sodium borohydride is the most mild form of H minus. And that the more mild things will only react with these stronger electrophiles, because remember, this is a nucleophile. It's going to react with electrophiles. It's only going to reduce ketones and aldehydes. We'll see that there are other, once we get further into the chapter, the other carbonyl type functional groups. Sodium borohydride is not strong enough of a nucleophile to reduce those. Okay, so because it is mild, sodium borohydride can be used with protic solvents. So one thing we've talked about before is that when we have strong nucleophiles, if we put them into something like, so an acetylide ion, that's something that we've talked about in this vein before. If you take an acetylide ion, a strong nucleophile, and you put it with water or methanol, that acetylide ion isn't going to be able to do the SN2 chemistry that we usually associate with the acetylide ions, because it's going to just deprotonate the water or the methanol or whatever the protic solvent is. But sodium borohydride is not like that. We can use it with protic solvents because it's a pretty mild reducing agent. So that's kind of all the kind of bullet points on sodium borohydride. So how does it work? Well, if we have this ketone or aldehyde, so I have R or H here. If it was R, it would be ketone. If it's an H, it would be an aldehyde. And we treat that with sodium borohydride. How does it react? What's our protic solvent? We'll just choose methanol. So that would be CH3OH. That's our protic solvent here. So how is this going to react? Well, we said that sodium borohydride is essentially H-. So we can draw our H- over here. We'll put it in quotes because it's not exactly H-, but that's how we're going to show it react. The H- is attracted to the partial positive charge on that carbon. Remember, we have a polarized bond here, and negatives flow to positive. So how mechanistically will this work? Well, the negative charge will flow to that positive charge on the carbonyl carbon. What else do we need in this mechanism? We need another arrow right now, right? What is that? Make sure you can think that through. Pause it if you can. Think about it for a second. Yeah, we can't, you've unpaused. We can't just make a new bond to carbon. We have to break a bond too, because carbon can't have more than 4 bonds. So those electrons go up to the carbonyl oxygen. That gives us this alkoxide here. And what is CH3OH? Again, that's our solvent. There's always hundreds or thousands or millions of solvent molecules for every one molecule of our reagent, of what we're trying to, of our starting material. So there's a lot of these around, and CH3OH has a mildly acidic proton, right? This proton here on methanol is mildly acidic. You should know that pKa. What is that pKa? Good job. Yeah, the pKa of an alcohol is about 16. So when we have this alkoxide here, it can deprotonate that alcohol. And what kind of arrows should I? So the product at that point would be this alcohol. But what kind of reaction arrows should I have there? Should they be equilibrium arrows? Should they be equilibrium arrows going more to this side? Should they be equilibrium arrows more going to that side? Equal equilibrium arrows? What should it be? Yeah, it should be equal equilibrium arrows, right? Because this OH is an alcohol. It's going to have really similar acidity to that alcohol. So essentially, both sides would be represented. So how are we able to make this as the product and purify that by itself then? Well, it's all about the amount of stuff around, right? If there are 1,000 or 1,000,000 of these, for every one of these, it's just going to happen that this is going to come into contact with that and transfer a proton. So if that happens because there's a lot of those around, then that's going to push the equilibrium to that side, essentially Le Chatelier's principle. So that's how sodium borohydride works. So we'll talk more about more reagents soon.